The general purpose input core is the second simplest, or actually it's as simple as the general purpose output core, and I recommend that you watch the general purpose output core as well as an example. But in here, we're showing you the way that actually the processor reads from it. Its purpose, its ultimate goal, is to let the microprocessor communicate with the rest of the world by reading something from the rest of the world, and that something is going to be connected to our switches on the board. So the general purpose input in here, we need to design the circuit for it. And if you're really designing the circuit, it's frankly speaking just a register, and that's about it. It's actually a register. Whatever you put in the switches gets stored in it. That's basically the custom logic that we have it. So the next step after we design the custom logic is actually to figure out the I/O map, or the register map basically. And the register map, we know that our register map should be something like this in here. This is my map, for example. And what I have is I have about, let's say, 1, 2, 3, 4, 5, and it's like I have 32 rows. And if I'm thinking about it, my register map should only have maybe half of them, because each one of them is 32-bit and I have only 16 switches. So my register map tells me you just need the first half of the very first register, and that should be it. And that's just reading, because you're just reading it. The processor only reads it. Okay, so now we have the register map. The next step is to design the wrapping circuit around it, so we can actually connect it to the MMIO controller and connect it to the rest of the system. And that is what you see in this code in here. So we have the clock on a reset because our custom logic needs it. Okay, and then the next thing we have is actually the interface law. This is actually shared among all of them. This conformity actually makes our life easier in designing these wrapping circuits. Next, we're going to have to decide whether there are external signals or not. In this particular core, we do have an external signal, so we're going to expose it to the rest of the world called DN. And now we take a look at the code. The code itself is it's a register. This is the custom logic. This is what it's telling me in here. And now, because I know that my register map is just reading, that means everything I'm doing is just multiplexing. But frankly speaking, I don't need to multiplex anything because I only have one register. So there's no need for me to do any multiplexing. Just as a reminder, the second level of multiplexing or decoding or whatnot is already incorporated in the MMIO controller, which is actually in a separate video. Okay, so what we need to do is now figure out how we can actually take this and send it to the processor. And it's really simple. It's right here. There's no multiplexing because there's only one register. There's a couple of lines in here. It might look confusing. And the reason why is I just want to make sure that I'm only sending half of the word in here. So the data, the data that we're sending on its output, the read output that gets multiplexed all the way to the FP read data, the one on the bus, is actually we're sending the first half. We'll just take whatever we put in that particular register in here. And then the next half, which is the one on the top, is actually we're putting zeros because I don't need any of these in here. So remember the processor reads in a chunk of 32 bits at a time or something like that, okay? And the W is specified as a parameter. 8 is here because some of the boards actually only have 8 switches. Ours have 16, so you can actually just specify this to be 16. And that's as simple as it is. Of course, the next step would be after you all do all of this and you connect it to the MMIO controller, you need to derive some sort of a software driver using a C++ code, which we already covered.